So in the two-layer structure, one of the first concerns we had was that the distance, the vertical distance from the top electrode to the bottom electrode was going to be very short, especially in comparison to the lateral distance from the tip of one electrode on one side of the trap to the tip of the electrode on the other side. So if this is a transverse view and the ion is right there, we define an aspect ratio as A divided by B. And so for a gallium arsenide trap, that aspect ratio is typically really high, where in comparison to some of the manually fabricated traps like the T-trap, that ratio is closer to unity. And so we were worried that as we have a high aspect ratio, our trap depth and strength might decrease to a level that's not acceptable for trapping. However, when we did simulations, we find that plateaus at a certain point. Actually, it's 1 over pi times the unity, the strength of a trap with a 1-to-1 aspect ratio. So that was encouraging. For the actual fabrication of this trap, this is going to be the two-layer structure. We start with an MBE grown structure that has alternating layers of highly doped gallium arsenide. So that's that layer and that layer. And in between are insulating layers of aluminum gallium arsenide, where it's 70% aluminum and 30% gallium. The first thing that's done is a backside etch, etches out all of the material below what will soon be the ion trap. And that's so that we can have laser access through the trap. So a laser will be shined from down here up through the trap. Next, a plasma dry etch, an inductively coupled plasma, is used to vertically etch down to be able to access the second layer of gallium arsenide to make electrical contact. Then this other bond pad out here, which is going to contact the substrate and ground it, is etched farther down in order to make that contact. Then the gold bond pads are laid down. They consist of a nickel, germanium, gold layer structure, and those are annealed so that the contact is good. That was done in an E-beam evaporator. And finally, the trap starts taking shape when all of the electrodes are laterally defined with another ICP dry edge. And then the last part is using hydrofluoric acid in order to etch out the aluminum gallium arsenide insulator that's near the edge of the trap. We do that so that if any charge builds up on the insulator, it's far enough recessed back into the trap so that the ion doesn't affect the ion as much, because it has all of this cantilever area to ground itself. This is an SEM picture of the gallium arsenide trap. You can see all the gold bond pads out here and the cantilevered electrodes. This is the hole, the backside edge hole that goes up through it, and this is the substrate ground right here. From a zoomed-in view, you can see the high aspect ratio of this trap. This was actually an earlier gallium arsenide trap that we didn't get to work. The distance from this cantilever to the bottom one is 2 microns. The trap, and we weren't able to apply enough RF voltage to that to get it to actually work. So after that part, we made another trap which had an MBE grown layer of 4 microns of aluminum gallium arsenide. And so we were able to apply more voltage to that structure and finally got it to work. And this is an image on the camera, on the CCD camera, of a single ion trap with this gallium arsenide trap. For the voltages that we used, which was about 8 volts and 16 megahertz RF frequency, the depth of this trap was about 3 times room temperature, and the secular frequency was 1 megahertz. So this was a relatively shallow trap compared to, for instance, the T-trap, which can be 40 to 100 times room temperature, depending on the voltage you apply to it.
When I look at the picture, so the things I see are gallium arsenide, you also etch the algas selectively?
Yes. The algas in this part right here. Okay, so in this backside edge right here, we were able to stop on that algas layer by using a Corona etch to get most of the way through the gallium arsenide, and then using a selective citric acid etch that had about a 61 selectivity, and then stop right on that algas layer.
And then, so you etched it looks like you also etched the algas, made a groove.
You can see it in the Oriu, yeah.
If
you look on the overview,
yeah,
right there in the lower left, you can kind of see
so
that.
why can't we move the outgas?
Wait, I'm sorry.
Where do you see the curve, the arc of the outgas under there?
Oh, this thing?
Yeah.
Oh, this is, I think that is more like a surface defect that we worked on taking care of. If you actually looked at, maybe I'm not looking at the right part, but if
you had ones that you can't see.
yeah, if you were to look through a light microscope, you would see these little curves right here that go like that.
So, but my question is, electrically, do you need to remove the outgas?
The point is that if it charges up and the outgas goes all the way to the edge here, and a little charge is on it, the ion will see that directly. Those field lines will have direct impact on it.
So you're talking about any insulator?
That's right. You want to get rid of as much insulator as possible. The lifetime of the ion in the gallium arsenide trap was significantly different than some of our other traps. If we just continuously laser cool it, we have a lifetime of about 25 minutes, or maybe less, maybe like 15 minutes. And so that sort of led us to believe that, well, either the heating rate of the ion in the trap or the low trap depth is a problem here. Actually, this data right here indicates that it's probably any time the ion in the gallium arsenide trap collides with background gas, it gets kicked out. And that probably isn't the case in a lot of our other traps where they can sustain a collision and stay there. So that's why we had a relatively low lifetime while being continuously cooled. Now, when the cooling beam is turned off and the ion is no longer being cooled, the lifetime in the gallium arsenide trap was also relatively short, about 0.1 seconds. So that indicates that there's a really high heating rate in this trap. And you can compare that to some of the other traps that are operated that are much, much larger, where they can trap an ion and turn all their lasers off overnight and come back the next morning and still see an ion there, even while it wasn't being lit. So this was an indication of what the heating rate would be. And we actually did some quantitative measurements on that, so I mentioned before that we couldn't do this Raman sideband thermometry technique because we weren't in the Lamb-Dickey limit with this trap. So what we did was we used nearly co-propagating Raman beams. They were separated from each other by about 7 degrees, and we looked at the suppression of the carrier transition. If you're well within the so this is not as sensitive a technique as what the sideband thermometry was, but if you cool your ion down and then measure the Raman transition rate for the first couple of microseconds, and then you repeat the same experiment where instead of measuring that transition rate immediately, you wait for a delay time of 1 millisecond, you can see that these transition rates are different. And so by plotting 3 of those different points, one with a delay time of half a millisecond, one with a delay time of 1 millisecond, and then fitting a line to it and comparing the intercept of that line with its slope, we can find what the heating rate of the ion is. And we measured it to be about 1 plus or minus 0.5 quanta per microseconds. When we put this in the context of all of the other traps that I showed in a previous slide, the chip trap is one of the smallest ones, but it's also one of the highest ones. So it's about an order of magnitude above the line that's drawn here. Now that isn't of particular concern because there are a lot of other outlying points that are above this line. And so while this noise is really high, it's not necessarily inconsistent with the size of the trap.